Okay, we're up and running. So first of all, sorry about yesterday. Um, and I looked more carefully at the assignment, and just so you know, I think I told it to you, but I'm going to tweak it a little bit. And this might, I know some of you might be upset because I might have just eliminated a problem or two that you worked on. Okay, so anyway, here's what the revised assignment's going to be. Down there on the bottom, I'm crossing out the 41 and the 47. And I'm going to at least start number 33. So I'm crossing out 41 and 47. So if you've worked on them, I didn't mean to disappoint you, but I just think there's enough problems here. Some of those at the end, they're just quite a chore to set up. The calculus isn't that hard, but the setup of the problem gets to be a real challenge. I'm going to show you for sure one of those big challenges today. Okay, let's get started then. So we did number 9 last time in class, but I didn't do number 10. I thought that would be a good warm-up for us, kind of. So in number 10, oh, did you guys want to ask any questions? Sorry.
You said we were going to start 33, right, eventually?
That's one of the problems I'm going to do during class today. Correct.
Because I guess my questions were just on those last, or the last two that you just mentioned. If we're
okay. Well, yeah, we're going to start number 33. I'm not sure if I want to do the whole thing for you, but we'll see how it goes.
All right.
Anybody else? All right, well, let's take a look at this number 10. In these two problems, we were supposed to find the length and width of a rectangle that has the given perimeter. And in this one, instead of a number like we did on number 9, this time we have just a letter, P, a constant. And it shouldn't really change the problem, but sometimes creates difficulty for people. So I thought we'd take a look at it. So we have a rectangle. And we've got a length and a width. And we know that when you take 2 lengths plus 2 widths, you will get the given perimeter P. Okay. Now, eventually we got to do a derivative when we do something, but we can't have, well, P is a constant. We don't have to worry about that. But we can't have 2 variables, L and W. So just like last time, we need to get rid of one of those letters. So how about if we solve for W? So if we go on here and subtract 2L from both sides, and then divide both sides by 2, let's see what we're best off doing. I don't know. Let's just write it at P minus 2L all over W. I'm sorry, all over 2. Okay, rusty. Yeah, let's rewrite that. So that would be P over 2 minus L. There we go. So now we've got an expression for W in terms of L. That's what we wanted. So now we should be able to go and do it's an area problem, as you can tell from up on top there. So now the area, of course, is length times width. So length times the width, and we want to use the new width. And I'm going to just call that f of L. That's the function we're trying to maximize. So now we take the first derivative. Oh, I really should multiply this out first. So let's do that first. So let's say P over 2, I'm going to leave it in this form. Minus L squared equals F of L. Now let's take the derivative. So here we're just going to get the constant P over 2 because we had a, first degree, and then minus 2L. Now we set our derivative equal to 0. And then we can add 2L to both sides. And L equals P over 4. Now, if you just think about it a minute, this shouldn't be too surprising. If you take the perimeter of a rectangle and say the length is 1/4 of the perimeter, in effect, what you're saying is this rectangle is best off as a square. And you've heard that before, that when a rectangle is in a square, it will have a maximum area. So this shouldn't be too surprising. What did we find out with number 9 yesterday? Let's take a look here. Yeah, we found out the length was 20, and sure enough, 20 is 1/4 of the perimeter 80. So, I mean, really, we got the same result yesterday. The only thing different about number 10 is we had to do it in more general terms. And so even when you're not given a number and we have just a constant P, we can still go at the same kind of problem. You'll have to, I got a couple timeouts here for blowing and coughing. I'm sorry. So, anybody have a question on number 10?
Can you just scroll down so I can see the work, please? Thank you.
You're welcome. No, I didn't write it out, but I might put on here, therefore, rectangle needs, having a little trouble with my pen, with my writing here. Rectangle needs to be a square to maximize the area. I mean, you don't have to have that in there, but I mean, that's what happened when we found out that the length was 1/4 of the perimeter, which means all sides are equal and it's a square. All right, let's go on to number 12. Next example. So this time, we're given an area and we're supposed to minimize the perimeter. So it's just a total, kind of the opposite of what we just did. Before, we were given the perimeter and we had to maximize the area. This time we're given an area and we have to minimize the perimeter. Okay, so once again, rough sketch, width, length, and this time we're given the area, A. So this is kind of the beginning relationship that we have given. And A is a constant, so we're not worried about that. But again, we have two variables here. We can't do that. So why don't we solve for W? If we divide both sides by L, we have a new name for W. So instead of the width and the length, we now have the length and A divided by L are my two dimensions. Now it's time to calculate the perimeter because, now we're heading for this minimum perimeter. Okay, so to find the perimeter of a rectangle, we take 2 times the width. Boy, having a little trouble with my pen. Excuse me a second. 2 times the width. Come on. 2 times the width plus 2 times the length. And that we'll just call F of L. Again, because L is really our only variable. Remember, A is a constant. We just don't know what it is. Okay. I should have probably written that a little differently. Instead of writing 2A over L, I could have written it this way. Okay, now let's take the derivative. So over on this first one, remember A is a constant, so 2A is a constant. So we do the power rule, we get negative 2A plus 2 equals the derivative. And okay, what did I do? Oh, we're supposed to, yeah. Okay, hang on, I'm goofy.
Wouldn't it just be over L squared?
Yeah, where did I mess that up?
Just,
Oh, I didn't lower the power by 1. Yeah, thank you. So this is 2A, negative 2A, and then this is L to the negative 2. So that is negative 2A over L squared plus 2 equals 0. And now you can subtract 2 from both sides. And we want to, of course, solve for L. Let's cross multiply. So negative 2A equals negative 2L squared. Divide both sides by negative 2. And finally, L so what we found out is, again, the same thing. If you want to do a max or a min in a rectangle, you always wind up with a square. So what's the length? The square root of the area. So from an area start, we wind up with, square root. When we did the perimeter, we found out, it's 1/4. But both things point to a square. So let me see, did I answer the question? It says, find the length and the width. All right, well, if the length is the square root of A, what is the width? Trying to get my pen to work. What times the square root of A would equal A, which is the area? It's got to be another square root of A. Because it's a square, that's no surprise. So both the length and the width are the square root of A. Okay. Again, you can't see everything, so I may have to scroll. Does anybody have a question regarding number 12? Okay, So now we're going to take a big leap here, and we're going to take a real challenging problem. This one's going to take a little while to show you, but it's, I don't know, it's the kind of thing that happens, and you have to be able to handle it. So I'm going to first take a look at the book. It's number 21. It's the one right, second one down from the left. Second one down in the left column. Maximum area. A Norman window. You see what a Norman, they've got a picture of it there. A Norman window is a rectangle which is topped off by a semicircle. It's the kind of window wives like to have put in their homes. It's attractive, and they're very expensive. So here's the deal. A Norman window is constructed by adjoining a semicircle to the top of an ordinary rectangle window. See figure. Find the dimensions of a Norman window of maximum area when the total perimeter is 16 feet. Now, I'm just going to tell you, that's not perfectly defined. What do they mean when they say the total perimeter is 16 feet? Do we have to do the perimeter of both separate panes of glass and add them together? No, they just want you to make believe that cross piece is not there. That's the way I did it. So in other words, the perimeter of this dome-shaped object all together in one. So I'm not saying one is right, one is wrong, but you've got to make some assumption to proceed, and that's an assumption I made. Okay, so here we go. So here's my picture of the Norman window. I've got the rectangle in red and the semicircle has a black border to it. The book told us this horizontal dimension here was X, and they told us to call this other rectangular value Y. And then, of course, this is what they told us. They said the perimeter is 16 feet. So I wrote that on the top. Now, let's see if you can tell what I was doing here. So if you take the perimeter like I did, that goes like this, it comes up, goes on, there's not this double, there's no bar on the left that we have to, there's no bar in the middle. I'm pretty sure that's what they meant. So what's the perimeter of that thing? Well, I've got two Y's, one on either side. That's why I have 2Y. And then I've got the X on the bottom. And then on the top, I have the what? Half a circumference of a semicircle? The length? Well, that's what this is. Let me explain. I don't know if you remember, the formula for circumference is pi times diameter. For a circle, the diameter here is X, so that should be pi times X, pi times diameter, pi X. But because it's only a half circle, I have it over 2. Okay, so if you add those all up, the book said it's 16. Okay, so that's kind of my beginning point right there. I have to start with a given perimeter. And from this, again, I've got a problem because I have two variables, X and Y. I've got to get rid of one of those. I decided to get rid of the Y. So you can see in my steps here, I tried to get Y by itself. So I first subtracted X and pi over 2X to get those off to the right, and then I divided everything by 2. So I now have this alternate expression for Y. Okay, so now that I've got a new name for Y, and we of course know X, what's the formula for the area of this Norman window? Because we're supposed to maximize the area of the window. So, well, you got a rectangle, which is length times width. That's this part, length, x times y. And again, in place of y, I use that new expression, so I don't have to deal with a second variable. And then let me explain this. This is what? The area of the semicircle, the area of that thing on the top. Okay, well, what's the area of a circle? Pi times r squared. And what's r squared? You know, you can see I did it up here, way up here at the top. See this? That'll help you see. So I took pi times the radius squared. Well, the radius is x over 2. And then why did I have to divide it by 2? Because it's only a half a circle. So pi times r squared cut in half. Well, when you put this all together, pi times x squared over 4 divided by 2, you get this. That's where I got the pi x squared over 8. Okay, so now we've got an expression for the area. Now it's time to what? Simplify that as much as I possibly can algebraically, with the intention of taking the derivative and setting it equal to 0 and solving. I'll just pause there. Did anybody have a question so far? This is kind of, just kind of complex, but I mean, the principles are pretty basic. So then if you just follow along here, I multiplied the x out times the parentheses here. And that gave me this expression. And then I did a little factoring so that I'm just trying to make, let's see. Yeah, so it's just a little bit easier. So in parentheses now I have the constant. See, there were 2 of these x squared terms here that I combined. Anyway, when you take the derivative of 8x is 8. And then here we have what? For this guy, we have a power rule, -2. Constant stays the same, lower the power by 1. And then for the last term, power rule, 2 times pi over 8 is pi over 4, reduce the power by 1. All right. So we're right here now. Now I take that derivative that I just found. Oh, I did multiply this -2 times that, and if you're wondering why this looks a little different here, I multiplied that out. But the big difference is I set it equal to 0. And so now the whole idea here is to solve for x. So it's a little bit messy. I subtracted 8 from both sides, and then down here I did this multiplication. X times -1 is -x. X times -pi over 2 is -pi over 2x. Anyway, when you take a -pi over 2x plus a positive pi over x, that gives you, so it's -1/2 x, -1/2 of pi x plus positive 1/4 of pi x is -1/4 of pi x. And finally, I could factor the x out, and you get this kind of an ugly expression, but there it is. X equals, that's the number I need. I worked it out, and it's a little bit less than 4.5 feet. So this one it's just kind of messy to deal with. Longer multiplication process. But I mean, the actual derivative wasn't that bad. I think it's more of an algebra problem than anything else. So now, if the original assumption I used was that the perimeter should only be around the outer boundary, then that's correct. And I believe that's what the book has. But they could have meant include these, and of course that would have been totally different. By the way, then the window would be considerably smaller because you'd have all this extra perimeter. 16 feet would have to be jammed into not only outside, but twice that bar going across. And the ladies wouldn't be as happy because their Norman window would be considerably smaller. Anyway, I know there's a scrolling problem here, so I don't know. I'll linger on the bottom here. My guess is that's maybe where some of you were not able to catch up. Let's see if there are any follow-up questions there. I will be publishing not only the video, but the updated 4.7 notes. So you can get your eyes on this just a little bit after we're done today. All right, I want to get going on one more. I want to pick number 33, and this is one of your problems. And I don't know. I honestly don't know how far I'm going to go. I'll finish it. Maybe we'll just get started here and let you finish it. Let's see how it goes. So it's a minimum surface area. You can see a solid is formed by adjoining two hemispheres to the ends of a right circular cylinder. Oh boy. So it's like a can with almost like a half dome on the top and a half dome on the bottom. And the total volume of the solid is 14 cubic centimeters. Find the radius of the cylinder that produces the minimum surface area. So again, we're starting with volume. And we got to end up with minimum area, surface area. So we got to deal with a couple different. So first of all, here's my, I don't know, it's not the great, I'm not the greatest artist, but you see how I tried to draw a cylinder with some half dome, half a sphere, hemisphere on the top and a hemisphere on the bottom. Almost looks to me like a sausage or something. Anyway, the volume is given to be 14 cubic centimeters. So now I gotta put that into the volume. How do I find the volume of this crazy thing and set it equal to 14? Well, the way I taught it in my students, pi r squared h, that's this guy. That's the cylinder. So a cylinder is the area of the base times the height. Well, the area of the base is a circle, pi r squared times the height. So height is, this dimension. The height of the can part. Okay? And then I've got two hemispheres. Well, wouldn't that be the same as one sphere? And the volume of a sphere is 4/3 times pi times r cubed. Okay, so if I add those together, that should be the volume of this thing. Okay. So now we're down to variables again. R is what we're trying to figure out, right? It says find the radius. So we obviously want R to be in there, but we can't have that second variable h. So now what I'm doing in these two lines is I'm just trying to get to a point where I can get the h, solve for h, so I can use a substitution. So I subtracted 4/3 pi r cubed from both sides, and then I divided both sides by pi r squared. So h would be by itself. I mean, first, what's this divided by pi r squared? Well, all that would be left would be the, the negative 4/3 and the r. And then this divided by pi r squared, well, I just put it over pi r squared. So now we have a height that only has r's in it. This is what we needed. So let me pause there. Does that make sense? So what am I going to do next? So we found a way to find the height. Now this becomes surface area problem, as you can tell. Minimum surface area. Okay, how do you find the surface area of this sausage? Well, a cylinder is just like taking a piece of paper and roll it up. I mean, it's just length times width, where the length is the circumference of the circle. So the circumference times the height. Okay, so what's the circumference of this? Hang on a minute. Yeah, that's not right. This is the surface area of a sphere, 4 pi r squared. And since we have 2 hemispheres, that's correct. And here's the height. Remember, we just found it up there. But this should be the circumference, pi times 2r, not pi r squared. So now it just becomes a matter of algebra to try to get, I mean, now you just, and this is going to be wrong because I had the wrong thing in there. What did I say? Pi r squared. Yeah. So that should be the circumference, right? So the circumference is how tall the sheet is when you cut it and fold it, flatten it out. So that should be 2 pi r or pi d. 2 pi r is the way you want to do it. Okay, so basically, now simplify, take the derivative, set it equals 0, and go from there. I'll let you guys finish that one, number 33. So it kind of got, I don't know, I think we got over a tough part there. So please note this correction. You should have 4 pi r squared plus 2 pi r times the quantity, negative 4/3 r, plus 14 over pi r squared. And I would next multiply that distributive property out, get it as simple as you want to get this thing as simplified as you possibly can before you have to take a derivative. Questions? So those are the added examples I wanted to give you. We didn't have time for the other day. So I'm going to let you guys finish that one. And that'll be it. I will publish, I'm going to redo the rest of this problem because of that mistake there. And then I will, I'll get the video published in just a short time, and then I will redo my notes here, and then I'll publish the 4-7 notes. I had them up already, but now we have additional examples added on. And again, anyone have any questions? Okay, then I look forward to seeing you tomorrow. Have a good one.